Okay, well, it's a real pleasure to introduce Sukruti Bansal to give today's seminar. She's joining us from Karlsruhe. We are still online, virtual. So, and she's going to tell us about Stückelberg unimodular versus Goldstino Brane approach to de Sitter supergravity. Okay, excellent. Thank you. I hand it over to you.
Thank you. And I want to thank Denja and other organizers for giving me this chance today to talk on this topic. I know the title looks a bit intimidating, but I will explain it soon, so it'll be look simpler. This talk is based on work, some work that has already been done, and the rest of the work is in progress with my collaborators, Sylvia Nagy, who is at present at Queen Mary University of London, but she'll be joining DIAS soon. Then Tony Padilla at the University of Nottingham and Yvonne Zavala at Swansea University. So these names that you see, Stückelberged, Unimodular, and Goldstino Brane, these are basically just different names. I'm hearing some background noise.
Oh, I will get rid of any of those noises. Let me quiet anyone that's unmuted. They can unmute themselves. Actually, my one is.
Okay, thanks. So yeah, as I was saying, these are different approaches for constructing models of pure de Sitter supergravity. So let me first begin with why we need de Sitter supergravity. As we know, over the last couple of years, a lot of observational data has given us evidence telling us that our universe is expanding at an accelerated rate. And one possible way to explain this accelerated expansion is to consider de Sitter supergravity, which is the maximally symmetric solution of Einstein-Hilbert gravity with a positive cosmological constant. Now, until a few years ago, if we were to consider a simple supergravity model for n equal to 1, it was possible to get de Sitter supergravity using Minkowski, to construct supergravity models for Minkowski background or anti-de Sitter background, but not for a de Sitter background. So it was a problem. So let me show it a little more explicitly what the problem was. Now, if we look at a generic de Sitter or anti-de Sitter algebra, particularly the commutator between the translation generators, we see that these the translations don't commute, but instead they give this Lorentz generator here. And there's this constant S sitting here, which takes different values depending on whether the solution is de Sitter or anti-de Sitter. Now, this here is a generic linear supersymmetry algebra for n equal to 1. Here, Q is the supersymmetry generator. P's are the translations, and M mu, as I already talked about, it's Lorentz. Now, here the translation generator, the translations commute. When we try to embed the de Sitter or anti-de Sitter algebra into a linear supersymmetry algebra, and then compute the Jacobi identity, which is supposed to be obeyed by the algebra, which is this identity. Basically, you can put more commutator brackets here, and when you expand the identity here, we find that this constant S takes the value +1, which corresponds to ADS spacetime, so a negative cosmological constant. So it shows us that at least in 4 dimensions, for n equal to 1 supersymmetry, de Sitter superalgebra does not exist. So if we want de Sitter superalgebra, we need to break supersymmetry, or in other words, realize it nonlinearly. Another point I want to emphasize here is that we are particularly interested in pure de Sitter supergravity, which means that supergravity which is not coupled to scalar or matter fields. So pure DS supergravity was realized for the first time in 2015 by Bergshoff and collaborators. And soon after, there were some other groups also who came up with different methods of realizing the supersymmetry nonlinearly. these are the different methods here. Now the first one is called nilpotent superfields, which was used by Birkhoff, Friedman, Kalosh, and Brane. I will show these names again shortly. And soon after, which was later in the same year, other group of people based in Padua, Bandos and collaborators, they used what's known as a Goldstino brane for constructing a non-linearly realized n=1 supergravity action. And then sometime after that, my collaborators, which are Sylvia Nagy, Tony Padilla, and Yvonne Zavala, they constructed what's known as the Stückelberged unimodular supergravity model. So these are all different models for n=1 pure de Sitter supergravity. So some of the questions that I will address in this talk are what these different methods that I just mentioned, what are they? I will try to describe how these methods work. And then a natural question to ask is that these different actions that we get using different methods, are they physically the same, or are they really fundamentally different? And since these actions can be very complex, not just because they have different notations being constructed by different people, but even otherwise they are quite long actions, it's not easy to compare them. So what kind of techniques could we use to bring them in a form such that we can compare them? First, here I'll give a brief historical review of the work that's been done in this area and related areas.
Can I interrupt?
Sure. Yeah.
The first thing is, I am puzzled by de Sitter for a couple of things. First is there is no scattering in de Sitter. So one cannot address any physical issue unless one has a scattering theory. But there is no scattering theory because of horizons in de Sitter.
Okay.
So I don't know whether these algebraic approaches, infinitesimal approaches, address this issue.
Okay.
My first question. Second question is are these things supposed to apply for a whole universe or just microscopic experiments? For example, Minkowski generally is not thought of as applying to the whole universe. Here it seems like people are talking about the whole universe. I don't know what that means.
Okay, so
I don't understand this whole thing.
So to the first question, you're saying that it's not possible to have scattering in a de Sitter background. Now that is something, I mean, as it is, even at this stage, we don't know if these de Sitter models that we have constructed, they will ever actually explain the physical universe, or they are completely hypothetical models that we are playing with. It's too early to say that. But the main motivation for which we are working and constructing these models is that, I mean, they have the potential to explain why the universe is expanding. So basically, why de Sitter? It's because it gives this positive cosmological constant, which gives the repulsive dark energy, which has the potential of, by potential, I don't mean the physical potential, but the English potential, as in it can possibly tell us why the universe is expanding if there is a repulsive dark energy represented by the positive cosmological constant. But of course, I mean, as to the question whether these models can ever be physical if there is no scattering possible, that's a question I am unable to answer. I don't know about that. And your second question about whether I'm talking about some localized, some very small area, or the entire universe, I am talking about the entire universe and not some local or flat area like Minkowski. And the reason why I'm trying to model the whole universe is because I'm trying to explain the expansion of the whole universe, which is happening at a large scale.
But such considerations involving also quantum theory, do they apply in the whole universe like this? I don't know. Okay. We don't know anything about the whole universe. All kinds of issues arise. No, who is observer in the whole universe, for example?
Okay.
Yeah. Well, but they could tell us about the end state of the universe. The de Sitter expansion looks like it's going to last forever. So what's going to happen in the end state?
Yes.
Okay. Yeah, so please feel free to interrupt me at any point. Okay, so first these were the 4 people who gave a pure d-zeta model for the first time in 2015. And they used what is known as nilpotent superfields. I will shortly explain what they are using superconformal methods. And later in the same year, there was this other group of people, Bandos, Martucci, Sorokin, and Tonin, all based in Padua, who constructed pure d-zeta supergravity using what they now call a Goldstino 3 brane, coupled minimally to supergravity. Around the same time and in the years following their work, a lot of other work has been done in related areas, like exploring the properties of nilpotent supergravity, scanning the supersymmetry breaking scale, and the gravitino mass, and coupling pure d-zeta supergravity to matter, and studying the properties of constrained superfields and other such things. So these are only some of the names of the people who have worked on these things. I mean, it's not possible to list all the names on just one slide. And then this work has also found many applications in cosmology, because it has been possible to construct many inflationary models in cosmology using these d-zeta supergravity models. And though the immediate focus of this work is on supergravity, in the long term, we hope to be able to make some progress in the search for d-zeta vacua in string theory. Now, when we talk of d-zeta vacua in string theory, the first thing that comes to mind is the KKLT models, in which the key ingredient is the uplift from an ADS vacuum to a d-zeta vacuum by introducing an anti-D3 brane. And in recent years, a lot of progress has been made in understanding the role of the brane in constructing these d-zeta vacua. So it has led to the construction of a lot of different brane models. And here are some of the people who have constructed these models. So here's a brief outline of this talk. First, I will talk about the method used by Birkshoff and collaborators for constructing pure d-zeta supergravity, then by Bandos and collaborators. Then in order to explain the third method, which is a very different method used by my collaborators, I will first explain a simpler theory of unimodular gravity as a stepping stone. And once I have shown the constructions of all these different actions, then I will try to show how to compare them. And then I will talk about the work that we are doing at present, and we'll end it with the discussion. So this is the method for constructing pure d-zeta supergravity by Birkshoff and collaborators, who were the first ones to give it. And they start with 3 different multiplets. Here, a chiral compensating multiplet, which has a scalar field x0, a spinor chi0, and another scalar field f0. Then a nilpotent chiral multiplet S, which has these components, and a Lagrange multiplier multiplet. So the first and the third components are always scalar fields, and the middle ones are fermions. So here is a schematic form of the Lagrangian that these people gave. The subscript F here stands for the F component, which is the theta square component of the superfield. So this is what the Lagrangian looks like schematically. Here, this curly W is the superpotential. It has these constants A and B, which are arbitrary. They are not necessarily real. They can be complex. They can have imaginary components. And till as long as this Lagrangian has this Lagrange multiplier lambda, supersymmetry is realized linearly. But we want to realize it non-linearly, so we need to eliminate this Lagrange multiplier. For that, we vary over this lambda, which means that I solve the equation of motion of lambda. And that gives me a constraint on the nilpotent chiral superfield. So here, this is a multiplet. As a superfield, it looks like this. These are the components x1, g, and f1. So eliminating the Lagrange multiplier gives this constraint on the superfield, s square equal to 0, and that's why it's called a nilpotent multiplet or a nilpotent superfield. And this constraint gives this relation between the scalar field x1 and this fermion here, G. Now, using this relation, we can eliminate the scalar field. And once we do that, the supersymmetry is said to be realized nonlinearly, because that is how nonlinear SUSY works. So initially in supersymmetry, in linear supersymmetry, every bosonic particle has a fermionic partner superparticle, which is a partner. But in nonlinear supersymmetry, you have this fermionic particle Goldstino, which does not have a super partner particle, but it transforms into a bosonic bilinear, which is composed of that Goldstino itself. I will explain it a little more explicitly in some of the coming slides. So any case, when the superpartner of this fermion G is eliminated, supersymmetry is realized nonlinearly. And it also gives the value for the constant, the cosmological constant lambda, like this, in terms of the constants A and B, which appeared here in the superpotential. And since they were arbitrary constants, either of them can have a higher magnitude. And that's how we get this pure supergravity theory, which allows for both de Sitter and anti-de Sitter, and also obviously Minkowski solutions. So this is the approach that was used by Berkshire and collaborators. Any questions so far?
Yeah, just, I mean, this is a, as you presented, it is a model for a supersymmetric scalar field on a single supersymmetric scalar field, right?
Supersymmetric scalar field.
There's only, you've only produced one superfield.
No, there are these other multiplets also, which can be written as superfield.
Oh, yes, but if I just concentrate on the one supersymmetric theory, which just this S, what theory does it give rise to if I look at it in 4 dimensions?
This is n equal to 1 supergravity, pure supergravity.
Oh no, if I shut all the other fields off, I should still have a super. And if I just take this superfield,
yeah,
and I put that constraint on the superfield, it's going to give me some nonlinear sigma model type field or something like that.
But this is the Lagrangian, and it has the components from other superfields. So you can't have a Lagrangian which comes only from this superfield.
Okay.
Because this X has this index I here, and I is not just 1, but it can also have the value 0, which sits in the chiral compensating multiplet.
Okay, so I can't restrict just to the chiral multiplet.
No, not just to the nilpotent chiral multiplet, because these other multiplets or these other fields, superfields, are also contributing in the Lagrangian.
Okay, I'll come back to it maybe because I don't quite understand. Okay, right.
Okay. So, okay, this was the method used by Berkshire and collaborators. Now I will explain another method, which was used by these people based in Padua. Now, so their action can actually be written as a sum of 2 different parts. The first one is this one, the SG stands for supergravity here. So the first part is the standard pure supergravity action. Here, kappa square is Newton's constant. This coordinate Z is actually a super coordinate, and this takes 8. There is the dimension 8 because there are 4 space-time dimensions, 2 chiral coordinates, and 2 anti-chiral coordinates. So in total, there are 8 different types of coordinates. And this capital E here is the invariant 1 form, the form that is invariant under all the supersymmetric transformations within this superspace. And its superdeterminant is known as the Berezinian. So this is a standard pure supergravity action. Then the second part gives the negative cosmological constant term, or the ADS term. Here, this coordinate xi L is the, it includes the usual space-time coordinates plus chiral coordinates. So over here, or you could say the left chiral coordinates, these coordinates do not include the anti-chiral or the right chiral coordinates, but then you have this Hermitian conjugate here. And now this third part is the most interesting one, because it is this term which breaks supersymmetry and gives the positive contribution to the cosmological constant. Here, f square is the supersymmetry breaking scale. Now this coordinate xi here, it is the coordinate of the 3 Brane world volume. And this brane has come to be known as a Goldstino brane because it eventually gives the Goldstino fields. And so this brane is coupled to supergravity, and that coupling happens by embedding these world volume coordinates in the superspace coordinates like this. So these are the superspace coordinates, x mu, theta, and theta bar. And when they're written as functions of these 3 Brane world volume coordinates, the Goldstino brane gets coupled to supergravity. Now, one of the main reasons why we took a lot of interest in this action was that these people constructed their action using Weil spinors, whereas Birkhoff and collaborators used Majorana spinors. And the super-Stückelberg action that my collaborators and I work with also uses Weil spinors. So it is more convenient for us to compare our action with this action rather than the one given by Birkhoff and collaborators. It was shown by these people that this action is equivalent to the nilpotent superfield action given by Birkhoff and collaborators via field redefinitions. So we can choose to compare our new action with either of the 2 actions, and we will know that it will the result will hold for both the actions. So okay, the construction for the Goldstino brane action does not involve any nilpotent superfields to begin with, but when we solve the equations of motion for the auxiliary fields, we find that they do belong to nilpotent superfields. Anyway, that's like a trivial detail. The main thing to take here is that if we perturb the action up to the 3rd order in field fluctuations, we get this form. Now you don't have to look at it very carefully right now because it's a little long, but there are 2 main fields present here, like the psi field, which is the Gravitino, and this field G hat, which is the Goldstino. Now this is what the Goldstino brane action looks like. This is something to remember. I will come back to it later when I'm trying to compare this action with the super-Stückelberg action found by my collaborators. So this is, I'll just give a very quick overview of how a Volkov-Akulov action is constructed. I think I probably forgot to mention here that this part here, determinant of this bold E, this is a Volkov-Akulov construction where you construct a supersymmetric invariant one form and then take its determinant, and that realizes supersymmetry nonlinearly. So Volkov-Akulov actions are, I think, quite well known for realizing supersymmetry nonlinearly. So the simple step is to first write down the supersymmetric transformation for a spacetime coordinate x, say, like this, where epsilon is a SUSY parameter, theta is a Grassmann coordinate, and this is how the coordinate transforms. And then we just replace this coordinate by the spinor field chi of x. And this is what delta xa becomes. And this is how delta chi alpha is given. Now, the important thing to see here is that chi alpha is not, this is epsilon alpha, it's getting shifted by the SUSY parameter epsilon alpha, which is a constant parameter. But it's not transforming into another bosonic particle as such. It's I mean, it does not have a bosonic particle superpartner. On the it has this thing, this bosonic bilinear, which is composed of this Goldstino field itself, like chi bar partial chi alpha, or chi with these other things and partial chi alpha. So the bosonic bilinear that's appearing is composed of this Goldstino itself, and this is how nonlinear supersymmetry works. And then these are some details that can be skipped. This is, it obeys the required supersymmetry algebra. And then we take these infinitesimal generators, which are written in terms of the exponentials of the translation and supersymmetry generators. And this G inverse dg is a Moreau-Cartan one form, which is invariant under the supersymmetry transformations. And it takes this form. So basically, there are these generators, and then they have some other fields as coefficients. And the coefficient of the translation generator is this. And when we take its determinant, it gives us the Volkov-Akulov action. This is like a very generic way of constructing a Volkov-Akulov action. And this is what goes into the construction of the Goldstino Brane action. Okay, so those are the two main methods that were used for pure DS supergravity. Now I will come to a different method that was used by my collaborators. But before I move on to the main construction, I'll give a little bit of background, which is easier to follow. So we all must be familiar with the usual Einstein-Hilbert action, which is just square root minus GR. And then if we add this Lagrange multiplier term, we get what is known as the unimodular gravity action. Now here, we can eliminate the Lagrange multiplier by solving its equation of motion, which gives us this constraint. Now, unimodular gravity is like a gauge-fixed version of standard Einstein gravity. Gauge fixing in the sense that it's like you are setting the determinant of the metric to be a constant. Now, so basically what we have done here is that we started with the Einstein-Hilbert action and then we added two terms to it. Now this term, which is lambda times the Jacobian, it is invariant under diffuse because a lambda transforms as a scalar field, which is like this. But this term, which is lambda epsilon naught, it breaks diffeomorphism symmetry. So we need to find a way to restore that symmetry. And for that, we use the Stückelberg procedure. There are two ways in which we can perform these transformations. One is the active and the other is passive. In active transformations, it is the fields that are transformed.
So
and
just
sure.
Yeah, you've broken it down, the diffeomorphisms down to volume preserving diffeos. Is that correct?
Yeah.
You still have, that's what's left is volume preserving diffeos.
So yeah, I should have mentioned here that this action is still invariant under a subgroup of diffeos, which are known as transverse diffeomorphisms. So it's not like it's not invariant under any diffeomorphism transformation.
And are transverse diffeos the same as volume
so
preserving?
transverse diffeos are like, I mean, if your diffeo parameter is say xi mu, then divergence of xi mu equal to 0. When you have the condition on the transformation parameter that the divergence of the transformation parameter is 0, then that's transverse diffeomorphism.
Okay.
It is invariant under unimodular diffuse, no?
Invariant under unimodular diffuse. Yes, right.
Like that.
Yeah.
All right, thanks.
Sure. Because the change is a determinant of the transformation, the Jacobian of the transformation.
Yeah.
And so if it is 1, if you always choose it to be 1, that's a group. And one can, this object is invariant under that.
If I, basically this Lagrange multiplier is present before solving the constraint. And if I have not solved this, if I don't have this constraint, then I don't have this condition that it is, that the determinant is constant. I mean, at this stage, before I solve for lambda, this is the determinant is not constant. So the fact that diffeo symmetry is getting broken is not getting affected by the fact that square root minus g will later become constant.
I understand. But as is, that whole S is invariant under, it seems to me, and the Jacobian is 1, or the diffuse are 1.
Yeah, right.
As is, okay, without any action, variation or anything.
Yes. Yeah. So the value of this constant epsilon naught, it is often set to be 1, and that's why this action is called unimodular.
It seems like you spontaneously break the symmetry, right?
Yeah, right.
I see.
Yeah.
Or well, I think it's broken by hand. It's explicitly broken with the epsilon naught term.
Well, So this lambda comes with this condition, and of course you need both these terms at the same time. It's like adding a mass, when you add a mass term to an action and some symmetry gets broken.
Yeah, exactly.
Yeah,
So-
I would call that, yeah, spontaneously, but yeah, I see what you mean. Thank you.
Okay, so maybe I am getting confused between the terminologies.
Yeah, I'm using the terminology for particle physics. Yeah.
Okay. So yeah, I will first talk about the active transformations in which we transform the fields. This is the infinitesimal transformation of the Lagrange multiplier. Here, xi mu is the diffeor parameter, and these transformations are up till the second order in the transformation parameter. So now, when the field lambda transforms in the action here, we know that this lambda transforms as a scalar, but sorry, that was under general coordination. Sorry. Yeah, when lambda transforms and it differs, all these extra terms come in and they break the diffeor symmetry. So what we do is that we promote this diffeor parameter xi mu to a field phi mu, such that when you write this transformed lambda in the action, so over here what has happened is, over here there are these derivatives acting on lambda, but using integration by parts we can take the derivatives from lambda over to the parameters, and then when we write that those terms in the action and promote the parameter to the field, this is what the action looks like. And now when we perform a diffeor transformation on the field lambda, it's not just lambda that transforms like this, but also these fields phi, which transform under diffeors like this with the parameter xi. And the transformations of these two fields in the action are such that they cancel all the new terms that come in the action. And so the action again becomes diffeomorphism invariant. And that was using active transformations, but we can also use passive, in which we transform the coordinates. So here I'm showing more of a schematic representation. This is like the original coordinate, and it undergoes a diffeor to give x mu hat. And then we Stückelberg it to promote it to a field S mu of x. So this was a coordinate, but now this is a field. And then when we transform coordinates, we are supposed to include the Jacobian in the action and write the determinant of the Jacobian, and that is this term, determinant of partial s by partial x. And this is what the Stückelberged unimodular gravity action looks like. Now, this action is a full action in the sense that it's not showing you the terms order by order in fields or the parameters. But when I showed the infinitesimal transformations for active transformations over there, and there were these, like I showed terms only up to a certain order. So yeah, it can be checked that under the transformation of this field S like this, this action is invariant under diffeors. So that's how unimodular gravity works. Now, unimodular supergravity works somewhat similarly. We start with the simple n equal to 1 supergravity action. Here, this epsilon is the volume element superfield. It has these components, F0, F1, and F2. And there is this chiral superfield R. Now, F0 has this field, this Vierbein E. F1 has the Vierbein again and the Gravitino, and F2 has this scalar field, capital M star, which is an auxiliary scalar field. So these are the components of the superfield, the volume element superfield epsilon. And then I show the components of the chiral superfield R. The lowest component is the auxiliary scalar field M. And here, the spinor component also has this auxiliary field, which is a vector field, B mu. And then the Ricci scalar appears in the highest component here. So first I showed you the simple n equal to 1 supergravity action. And now, similarly to how unimodular gravity action is written, we write this Lagrange multiplier term in to get unimodular supergravity. Now these are all superfields. Lambda is a superfield, and these two are also superfields. This constant superfield epsilon naught has this expression. Here, the theta component, which is the spinor component, has been set to 0 for simplicity. So its lowest component is just the constant epsilon naught, and the highest one is 1/2 small m, which is a scalar field. Sorry, a constant. And the Lagrange multiplier superfield lambda has these components: lambda naught, lambda 1, lambda 2. And when we try to eliminate lambda, we get this constraint on the volume element superfield, which is similar to the constraint we got on the determinant of the metric in unimodular gravity. Now, again, here it's this last term. It breaks the existing diffeomorphisms. Again, here, there's a subgroup of the diffeomorphism symmetries with the transverse diffeomorphisms, which still keep this action invariant, but not all the diffeomorphism transformations have a symmetry for this action. Writing the components, the symmetry breaking terms quite explicitly in terms of components, we get this. And here, it's not just the diffeo symmetry that's getting broken, but also the supersymmetry. So now we have two symmetries to restore. Sorry.
Okay,
So
can I didn't get, so do you have also the Weyl symmetry? Because usually the transverse diffeos implies a Weyl symmetry. It's also broken, or you want to restore the Weyl?
I don't know about the Weyl symmetries. Yeah, I haven't thought about it.
In the sense that, you know, if the determinant is equal 1, then you can rescale like in a conformal transformation, and you can see that is, you know, the metric is also conformal invariant. That's why, so usually one can also think in terms of the Weyl symmetry, the unimodular condition.
Okay, so I don't see any reason why, why Weyl symmetry. Let me go to the simple example of unimodular gravity. So the determinant appears in these two terms, and if I rescale the determinant, now I already know that this term is breaking the symmetry, and rescaling the determinant for these two terms will not, I don't think it will break any symmetry for the action. So it appears to me that it's invariant under Weyl symmetry. It's not getting broken. Yeah,
exactly. So I was wondering if you want to, I mean, you do something on that. Because usually, let's say, conformal gravity is Weyl symmetric and implies something that is not in the Einstein-Hilbert theory. So, well, okay, we can discuss later. Maybe. I mean, I was just wondering if. Okay,
so you're saying that Weyl symmetry is an extra symmetry that is obeyed by conformal gravity, which is not necessarily. Present. Yeah. Okay.
Because usually, for instance, so if you do the higher derivative conformal gravity, you see that you can renormalize the theory differently from Einstein-Hilbert theory that you cannot renormalize, and this is just because there is this Weyl symmetry is a conformal symmetry. And
okay, yeah. So that's. I mean, it's quite interesting to know. This is something that I hadn't thought about before, but it's like maybe our Lagrangian has an extra symmetry that would be quite useful. Yeah.
Okay, thanks.
Thank you.
Why do you think why do you think there is a conformal symmetry there? I don't quite see it.
Because if the determinant is unitary, you can fix. Then you can see that under a Weyl transformation, that thing is invariant. So usually transverse diffeomorphism imply are connected to Weyl symmetry.
But Weyl symmetry should force me to scale the determinant.
Yeah.
So that I don't see the Weyl symmetry. I see that Weyl invariance is fixed.
Well, depends. No, depends. This is so. I mean, again, you can keep or you can break the Weyl symmetry. That is because there is also that you have the transverse diffeomorphism and also the longitudinal part. Okay, we can discuss later.
We should discuss it afterwards because I don't.
Okay, so here, as I've seen that this term, there are these terms which are breaking both the diffeo and supersymmetry invariance of the action, and I want to restore them. So I perform the Stückelberg procedure, and the Stückelberg transformations that we use are only up to the second order in the Stückelberg fields because we are using infinitesimal transformations, and so we have to stop at a certain order. Now, the xi mu is the diffeo parameter, and it is promoted to the field phi mu. And epsilon is the supersymmetry parameter, which is promoted to the field zeta. And then, as before, the transformed fields sitting here, like in these components lambda 2 and lambda naught, they are transformed under the diffeos and supersymmetry transformations using these parameters, and they are plugged into the Lagrangian. And then after they are included in the Lagrangian, we say that we are promoting these transformation parameters to fields like this. And then that Lagrangian is invariant under both diffeos and supersymmetry transformations. So I haven't shown the full Lagrangian, I've just shown it schematically here because the full Lagrangian is very long. But what's essential here is to get the idea of how the Lagrangian is obtained. So yeah, we also need to consider some boundary conditions on the Lagrange multiplier superfields. These are the simple conditions where the lambda naught and lambda 2, I'm not getting the word. They are the scalar fields, they go to constants at infinity, and the spinor component goes to 0. And when we do the Stückelberging, this is how the fields transform, and so the boundary conditions also transform, and these are just some transformed boundary conditions, but you don't need to understand it very carefully at this point because it's a little too involved. There are these functions y1, y2, y1, and y2 and gamma 1 and gamma 2, which are again in terms of the fields. So it's quite a long expression. So once we have the full Lagrangian, the natural thing to do is to compute the equations of motion and solve them. And we find that the equations of motion admit this set of solutions. Here, the vacuum expectation value of the metric G mu nu is represented by G mu nu bar. Then the vev of the scalar field capital M is given by small m. And these are the vebs of the components of the Lagrange multiplier components. And all the other fields that are not shown here, they just vanish in the background. So if we look at the equations of motion, we find that the cosmological constant is given by this expression here. And these constants K2 and K0, which were initially used in the boundary conditions, they are arbitrary. And so this expression can be either negative or positive. It can also be 0. So here we see that this theory allows for d zeta solutions. Now, this is quite interesting. And it also points at a fundamental difference between unimodular supergravity and unimodular gravity, because in unimodular gravity, the solutions were more or less the same as those of Einstein gravity. The only difference was that the determinant of the metric had been set to 1, but otherwise there was not much difference in the physics of the two actions. But here, in n equal to 1 supergravity action, we don't have any d zeta solutions, but unimodular supergravity action allows for d zeta solutions. So that's quite a big difference between unimodular gravity and unimodular supergravity. And yeah, so this is the third approach that was used by my collaborators for constructing pure d zeta supergravity. Now, I'll just show a very schematic comparison between the two actions, the Goldstino Brane action, which is this one given by these people. And this is the action that was initially constructed by my collaborators, but written in this form in our paper last year. Now, the first part of these actions, which are shown in green, they are the standard supergravity parts, and they match completely. They are exactly the same. I mean, I have not shown that very explicitly, but if you look at it closely, you'll find like over here you have 6 epsilon r, and same here. And here you have 2/3m, and so is it here. So these two parts are exactly the same. Now, the interesting parts obviously are the pure de Sitter parts, or the positive contributions to the cosmological constants. Now here in our action, this is what it looks like. In theirs, it looks like this. And they are both quite difficult and complicated to write down explicitly. And it's not easy to compare them. So we need to find some simple approach, simple method of comparing these two actions. And for this purpose, we resort to perturbation theory. So we start fluctuating the fields. So these are the fields in our system. There's a graviton, which has this background value, and this is the first order fluctuation, h mu nu. Then this is the spin connection. Then there are a couple of fields which vanish in the background, like the Gravitino, the vector field, which is an auxiliary field, b mu, and the spinor component of the Lagrange multiplier, and the Stückelberged fields. They both vanish in the background. They all have first order fluctuations though. And once we perturb and write the action, and if I just look at the fermionic part of the action for simplicity, this is what we get. And if we try to look at it closely, we find these terms inside the brackets, which are coupled to the Gravitino. And so we identify them as Goldstinos. We say that this is the Goldstino. And the mode orthogonal to this expression is denoted by tau. So using these field redefinitions, when we again express the action, this is what it looks like. Now, using the boundary conditions, it can be seen that the field tau actually vanishes, and it can be eliminated from the action, leaving us with just this action. And this action is exactly the same as the fermionic part of the action that comes from the Goldstino Brane action that was given by Bandos and collaborators. So it's quite nice. It shows us that at least up to the second order field fluctuations, the Stückelberged unimodular supergravity action is the same as the Goldstino Brane action. Okay, so are there any questions at this point?
Yes. So you're looking at the equivalence perturbatively. Do you have any idea what goes on at the non-perturbative level?
Not yet, but that is what we are working on at present. Okay. I will talk about it near the end of my talk because it is work in progress.
Okay, thank you.
Yeah. So, okay, so far so good. At least up to the second order of field fluctuations, they match. Now we go one order higher in field fluctuations. So if I want to write the action fluctuated up to third order in the fields, I need to fluctuate the transformations and the boundary conditions only up to the second order, because that eventually leads to the third order in the Lagrangian. So these are the modified boundary conditions, and I perform some field redefinitions. So this entire expression is just renamed as one field, and so with these two conditions. And but yeah, well, I mean, I used these simplifying field redefinitions for the boundary conditions, and yet now when I try to write down the full action perturbed up to the third order in field fluctuations, it gives this really long action, which is very nasty to look at. And obviously you don't need to try to understand it at this point, it's too big. So we need to simplify it. And for this, we try to do more field redefinitions. So there are a lot of auxiliary fields present, like the vector field b mu and these scalar fields m and m star, and then there are these Lagrange multipliers. These are the ones that came from the boundary conditions that I showed a few slides ago. So we do more field redefinitions. So this like small b mu is redefined in terms of this capital curly b mu and so on. And when I plug these redefined fields in the action and then again solve the equations of motion of these new fields, I get very interesting solutions. So all of these fields, they vanish up till the second order in field fluctuations, which provides a lot of simplification when writing the Lagrangian up till the third order in field fluctuations, I mean. So this is the action that we get finally after doing all these field redefinitions and elimination of the auxiliary fields. And this is exactly the same as the Goldstino-Brane action perturbed up till the third order in field fluctuations. Now, in the beginning, when I was showing you the Goldstino-Brane action, on one particular slide, I said that when we perturb the action up till third order in fields, that's what it looked like. And I said that I will come back to it. So basically, that action was exactly the same as this action. And it's very interesting to see that, you know, two actions obtained by completely different methods, not related, end up giving us the same action. So this is quite nice. Here, there are terms which are only leading order in the Goldstino field, G hat. At least up till this order in fluctuations, there are no higher derivative terms. It's possible if there were some higher derivative terms in the action, they would have been ghost fields.
Can you show us the Goldstino action again? Because
yeah, sure.
Sorry to.
No, it's okay. Actually, I mean, since that action was exactly the same as this one, oh. Yeah. So this is what the action was.
Oh, this is third order, but you had a non-perturbative form of the Goldstino action.
Yeah.
Is it clear that this breaks the full Diffio symmetry? It doesn't look like it does. It just looks like it affects the supersymmetry rather than the.
No, but even the Stückelberged unimodular supergravity action that we have constructed and we are working with.
This you was restored by this thing. Yeah, okay.
Yeah.
All right, yeah, I understand.
Okay, sure. Okay, so now it's interesting to see that these different actions are coming out to be the same. But there are certain terms like this one, which is given in terms of a different metric and these different gravitino-like fields, which was given by Volkov and Soroka many years ago, which are in principle possible to be present in the Lagrangian because they are invariant under all the symmetries that are present in the Lagrangian, and also they are not introducing any new fields. Like they are not forcing us to couple to some new scalar or matter fields. So they can very well exist in the Lagrangian in principle, but such terms do not show up at least via the constructions that I have explained in this talk. And the fact that such terms are not appearing, it indicates that these are possibly ghost fields, and the absence of such potentially pathological terms in all of these actions indicates the possibility that these different formalisms have some underlying theory, which probably comes from a more fundamental or more physical realization of the theory, say at higher energies like string theory. That's a question that is worth considering. Now, the Stückelberged unimodular supergravity action that I showed the construction and comparison of, it was all done using infinitesimal transformations for the active ones, active transformations. Now, if a natural question to ask is if all of these actions match at higher orders also. I have only shown that they matched at the third order field up till the third order field fluctuations, but what about full order? Or non-perturbatively, as Professor Nam questioned. So for this purpose, we are now trying to find a finite transformation for the fields. Here, initially lambda was transforming like this, where k is like a is given by this Km partial m, where it's a diffuse transformation operator. And this delta S is a transformation that acts on the supergravity fields present in the Lagrangian or whatever it's acting on. So this operator K mostly, it acts on the supergravity fields, while delta S acts on the, it acts on the Stückelberg fields, and this acts on the supergravity fields. Now, when we are trying to derive all these transformation rules, there are certain things to keep in mind, that lambda transforms like this as a scalar. And yeah, this is how XM transforms the super coordinate. Now we have reasons to believe that when we try to derive the finite transformation rules and operator, it might actually look like this. It is still under the checking process. We have to check it up at higher orders, but we believe that the finite transformation for the field lambda might look like this. Now it looks like a very simple generalization of this transformation, but it's actually, it's not all that simple when you try to check it by hand, because we need to check for certain commutation relations between this operator and this transformation, which in principle is not necessarily to be obeyed. So we are in the process of checking if this holds true at all orders. And if so, then we will have a transformation rule for finite transformations. And then we can perform the Stückelberging as usual. The differ parameter xi mu is promoted to the field phi mu. The SUSY parameter epsilon is promoted to the field zeta. And here the super coordinate xm it's just written as phi m after Stückelberging. Now, when we did the infinitesimal transformations for Stückelberging, the transformations of the Stückelberg fields were also written only up to a certain order. But now we will have to find the full transformation rules for the Stückelberg fields. And this is work in progress. Here delta K stands for the diffeomorphism transformations, and this one for Stückelberg transformations. I mean, the transformations that act on the Stückelberg fields. Because in principle, like when we begin with, the transformations they act separately. So yeah, this is all work in progress. And now we can also look at the passive transformations. Here, the super coordinate xm transforms like this under infinitesimal passive transformations. But it's possible that at finite order, for a finite transformation, this is how it transforms. Again, it needs to be checked. And after performing the Stückelberging, we write the Berezinian of the super Jacobian, and this is what the action looks like. I've already shown it before, but it's good to see it again now. And so if we look carefully at the Berezinian that is appearing here, this is what it looks. So this is the super Jacobian, which is written in terms of the derivatives of the transformed field with respect to the initial coordinates. And its super determinant gives the Berezinian. And this is the formula for computing it. I mean, though we know the formula, it's not very straightforward to actually solve it and get the answer. It can also be expressed as a superfield like this. And the expressions for these components S0, S1, and S2, they're quite long, so I have not shown them here, but they're there in the paper if you're interested. So now, one of the reasons that motivates pursuing these passive transformations is that the action, which looks like this, can possibly be expressed as what is known as the Hinault-Teitelbaum action for GR, which is somewhat similar in appearance to the unimodular gravity action. The main difference is that in unimodular GR, over here you have a constant, but here you have a total derivative of a field. So yeah, we are interested in expressing the Stückelberg unimodular gravity action as the Hinault-Teitelbaum action. And I'll tell why. Now, the Henau-Teitelbaum action can be re-expressed like this, where using integration by parts, I transfer the derivative from this field tau to the Lagrange multiplier lambda, and then write like this, where this field A, it's a 3-form, and it's a dual of this, a Hodge dual of this field tau mu that was sitting here. So now there's this 3-form appearing in the action, and it can help us connect or express the action as a 3-form supergravity action. Now, 3 forms are ubiquitous in flux compactifications in string theory. And if we have a supergravity action in 4 dimensions, and if we want to uplift it to higher dimensions, then the most suitable form is to use a 3-form supergravity action, because the field strengths of the gauge 3 forms can be identified as duals to the fluxes that thread the internal compactified space. So yeah, we are hopeful of expressing this Stückelberged unimodular action as a 3-form supergravity action. It will involve some dualizations. And we have had some success in this direction. So this was the Berezinian, and we wanted to see if it can be expressed like this as a total derivative of some field Tm, which will have these components where mu is the spacetime index and alpha is the spinor index, and these are the components. So we have been able to derive this field Tm up to a certain order in the field phi, which was the Stückelberged field, and there are these functions which are again composed of other fields. So yeah, we have derived the field Tm up to a certain order, and we believe that it might be possible to show the higher order terms using some generic formula for the nth order term. And the field Tm, it transforms like this under the full diffuse supergravity transformation. So it's good that we know how it behaves and how it transforms. So if we eventually succeed in completing all of this, we will have the Stückelberged unimodular supergravity action, the full action, the exact non-perturbative action, derived both via finite active transformations as well as finite passive transformations. And then we would like to compare the full non-perturbative action with the nilpotent superfield and the Goldstino Brane actions and see if they match completely. If they do, then that'll be very interesting, and it'll give us strong grounds for believing that all of these actions are coming from some comprehensive underlying theory, like some theory which holds at high energies, like a string theory model. But if we find that those actions differ at higher orders, then it will indicate some fundamental differences between them. And it will be interesting to explore the phenomenological consequences of those differences. And as far as the string theory model, a possible string theory model is concerned, such a model was already corroborated in a paper by the same group who gave the Goldstino Brane action. This was a paper following their Goldstino Brane action paper, in which they showed that when they couple their pure ds supergravity action to matter and then take special cases of that action, it matches certain parts of the 4D effective action for an anti-D3 brane coming from the flux compactifications of a 10-dimensional type 2b supergravity theory. And that type 2b supergravity theory is a KKLT-like model. And the anti-D3 brane is, it's constrained at the, strongly confined at the bottom of a throat. It's in a very strongly constrained region. So yeah, that's interesting to know that it's possible that there is an underlying string theory model after all. And so it will be interesting to uplift this 4-dimensional theory to supergravity, to 10-dimensional supergravity, and eventually find the string theory counterparts, if there are any. And yeah, it will also be interesting to use this pure d zeta supergravity action for constructing phenomenological actions in inflationary cosmology, because I think that there are quite many interesting models possible with it. And yeah, so this is as much as I have on this topic for now. That's all. If you have any questions, you're welcome to ask. Thanks.
Well, thank you very much for a fascinating talk.
Thank you.
It's, it is. I'm sure there are lots of questions. I have some of them. I will wait. The floor is open to questions.
So I'm wondering, how is the situation in 3 dimensions? So let's say that we go to more the topological gravity in 3D. Is there anything interesting there? I mean, starting from unimodular gravity in 3D and then you do the same steps?
I am not sure of whether anything of this kind has been constructed in 3 dimensions, and I'm not familiar with that work if there is, so I cannot comment much in this direction.
Okay, thanks.
Is there electromagnetism here in your model?
Not that I know of.
So my question is, let me ask. First, I am interested in the following issue. In these models, there should be a covariantly constant spinor to define supersymmetry. Is that not correct?
Yes, right.
So there is a covariantly constant vector field, which is null.
Okay.
Am I right?
So I'm just trying to go to the superfield, which will be covariantly constant.
Not superfield, I want spinor.
Oh, spinor. So, okay, so you're saying its dual would be covariantly constant.
So from the covariantly constant spinor, I mean, normally...
Well, that has to do with a particular background. So...
No, to define supersymmetry from what I know.
But not all solutions of supergravity will preserve supersymmetry. But if supersymmetry is preserved, then you will have a covariantly constant spinor.
That's correct. So, but I thought this is preserving supersymmetry.
Yes, it is.
Consequently, there should be a covariantly constant spinor. Am I right?
Yes.
So there should be a covariantly constant vector field, which is null.
Okay.
That's an issue I would like to know. Okay. So the class of metrics where this is allowed cannot be very broad. For example, d theta, I don't know whether it allows this situation. Okay. I think that the extremal black holes allow it, but I was discussing with Denjo. But to proceed further, from my point of view, one needs also a description of electromagnetism, let us say, or vector fields. I mean, gauge fields. I don't see gauge fields here, except for the metric. It's not a gauge fields. We need character forms.
Okay, so yeah.
So the real question is, how do I apply it to physics? Does it apply? Does it tell me about anything about dark matter, or even electromagnetism? What does it say?
Yeah, I cannot comment on that. It's not something I have thought about or explored.
So my issue is, what is the physics I get out of this? About physics means phenomenology. What can I check?
Well, yeah, I mean, this is not a phenomenological model. It's true that there's nothing observational in this model. And one way to connect it with phenomenology is to probably couple it with some scalar or matter fields. And in fact, the string theory model that was shown by Bandos and collaborators, it was an attempt to find a phenomenological model. And for that, they did some coupling with scalar fields. But until we don't do that, it's a completely hypothetical, theoretical model. And I don't know how to give any phenomenological implications at this stage.
suppose
So I cannot make progress, for example, with dark matter, or there is no engagement with reality. Am I right in these models?
Well, I think I can help with that.
Okay.
But yeah, so I'm a particle physicist, and to me, I just basically try to, stay alive. But I'm gonna let other people ask their questions. My questions and comments are going to be very, very naive and somehow lead to what Paul was asking. But yeah, I'll let other people ask their questions first.
By the way,
maybe I can just to clarify for 1 second, because I'm confused a little bit about the spin content of the model, and I would have thought it would give a hint as to how these different theories are related. Gravity at least has a spin 2 field in it, but you've also introduced now a vector field, an additional vector field, which I would have thought might look like a spin 1 field, but it has this weird gauge invariance.
Which field in particular? Which vector field are you talking?
Your capital phi, or your
multiplier field. That,
your Stückelberg field.
Okay.
You call it S mu. It's called S mu, I think, at one point.
Okay,
but it
so
will
you
not
mean
give any interaction. I mean, sorry. What I know about the Stückelberg field in, say, gauge series, we can introduce Stückelberg fields in gauge series. They only they give fake gauge invariance. You can put mass for the gauge field. Okay?
I'm familiar with them in that context, Bob, but I want to know what it's doing in this context.
So what I would I would say not to think of it as a vector field, but as a set of superscalars. So like this capital M takes 4 values or 6. No, actually it takes 6 values, 4 spacetime and 4 spinners. Sorry, 2 spinners. So it transforms as a set of superscalars rather than as a vector field. So I wouldn't consider it a vector field.
But then the action you wrote will not be invariant under diffuse. I thought
no,
that.
So the action is, it had the transformation. Okay, I will show.
It has a determinant of this Jacobian, no? Of the field.
Yeah. Sorry. I just. Yeah. So here you are saying that this. Yeah. If I do not consider this to be a vector field, that the action will not be invariant under diffuse.
Yes.
Okay, well, just a minute. I want to see the supersymmetric version of this action. Yeah, so I mean, this is still this is phi m is like a set of scalars. As I know, x mu is a vector. But the transformation of the field phi with respect to the initial coordinates is taken into account with this Berezinian. So, so basically, this Berezinian compensates for any new terms that come after transforming the coordinates.
If I go back to the way Bal was thinking about it as a vector field, as a Stückelberg, a standard Stückelberg field, I think of the standard Stückelberg field as a gauge field and a scalar field that multiplies. It's essentially the two of them together. But
okay, well,
for me, so for me, that spin content is a spin 1 and a spin 0.
Yeah, so the way I see it, at least, is that it's not a vector field. We are considering it to be a set of scalars. But at the same time, since we are using a Berezinian, we are ensuring that it's covariantly, the whole action is covariantly constant.
But sorry, but by the way, your presentation was very clean. I mean, very coherent. I just want to tell you that. Secondly, yeah, the diffuse relate not necessarily to these issues are not related to supersymmetry. It's just related to space-time diffuse.
Yeah, definitely. Yeah.
This object here, if it is, whether one puts it in superfield language or whatever, it's not gauged, it's not diffuse invariant unless that phi you wrote is a vector field.
So I am realizing now that for the case of Stückelberged unimodular gravity action, I did not show the passive transformation and the Berezinian very like on a separate slide. So anyway, at least this is the action and this is the field you're saying. So yeah, what you are saying that the diffuse are obviously not related.
Go ahead, Werner. You can clarify it for us.
I have another question. You had this potential term, psi, which didn't show up. And you said this is not because of any symmetry. Do you have any conceptual idea why the term is not there?
Sorry, which term is not there?
Just.
Did you get my...
I didn't quite get it, Werner. Can you try repeating a little bit of it again?
Repeat it. You had one term, G, psi, which did not show up, or psi tilde. Just go a bit further than still
Oh, okay, I understand. Are you talking about this one, right?
This one, exactly. Yes.
Yeah.
Do you have any conceptual idea why this term doesn't show up?
No. So yeah, it's a mystery, and we think that it might be, these fields might be ghost fields, and the actions that we have got, they are somewhat physical. Obviously, it's too early to say, but it's possible that those actions have a more fundamental underlying theory, and that's why they don't contain these potentially pathological terms. But other than that, I don't have any technical reason for why these terms are not showing up. I mean, the construction doesn't give us these terms, even though they obey all the symmetries.
Yes. So just a wild guess. We had a Schrödinger fellow until 2 years ago, now in Boston, who thinks that gravity, supergravity, should be understood as, in a way, as a product of two gauge theories. And that needs some constraints. Not everything can be written in this form. So, well, just a wild guess that you might think about such a kind of factorization, which might allow certain terms and others not.
Okay.
I think Sukriti is very familiar with this because she has worked with Sylvia and Liran and that group. So, yeah, that would be a very helpful comment, I think. Yes. Do you understand the comment, Sylvia or Sukriti?
I caught the part where he said something about like it could possibly, there could be a gauge product of two gauge theories.
He's suggesting that thinking of it from as a product of two gauge theories and some, I think, Lagrange multiplier fields that to enter in that setting might be a very productive way of looking at it. Did I summarize correctly, Bernard?
Yes.
Okay, thanks. Thank you very much.
Are you thinking about this developments of gravity as a square of Gauge theory?
Yeah, that's the context. She is involved at some level in that as well.
Okay. There is, may I interrupt again? One question, couple of questions. First is, the consistency of these models, I think they are quite difficult to check, but there are a variety of energy conditions in gravity, which are quite important positive energy solutions. For example, the Schoen-Yau proof of positive energy. Has anybody tried checking them?
If I remember correctly, the positive energy applies to de Sitter as well.
Yeah,
Or is
for
it-
that,
I am not aware.
No, is it maybe it's
positive vacuum energy.
Positive energy. I mean, there is this proof of Schoen-Yau and by Witten. Okay?
So for that, we will have to do a Hamiltonian analysis.
Yes.
Yeah, that's something that we can probably consider for our future research.
Has anybody checked whether the energy conditions are fulfilled by these models? There are Penrose's energy conditions and so on.
I'm not aware of it. I can try to check if such work exists.
Okay. By the way, you are from Ayuka, am I right?
No, I am from ISER Pune.
ISER Pune. Okay.
Yeah.
You were there when Paddy was there.
Yes, right.
Okay. Okay. I quit.
I mean, the relationship between the Hainaut form is intriguing to me, and I've always liked that particular one.
Yeah.
I mean, it will just as a tree form is the most natural way for me to think of it.
Yeah.
So you are optimistic that there is supersymmetric version of your model that's related to that?
Yeah, at this stage, it seems like. I mean, it was quite difficult even just to arrive at this expression for the field TM, even up to just this order. It took us almost a year to derive this. And in fact, this was what motivated us to instead switch to active transformations and start looking at those finite transformation rules, because we were not sure of how far this will take us. But now that we have this field up till this order of terms, it'll take some more work, but we might be able to get a general formula for terms of all orders.
Presumably, I mean, the Hainaut-Teitelbaum action is diffeomorphism invariant, is it not?
Yes, it is.
That's what I want to ask. Sorry about that. I was about to ask that. The expression looked like square root of G minus the total divergence of a vector field.
Right.
But the total divergence of a vector field is a scalar function.
Yes.
But the metric is not a square root of the determinant, square root of minus G is not a scalar function. It is a half density. There is a determinant that comes in the transformation.
Yes.
So why is this diffeomorphism invariant? This is Benjo's question put in another way.
I'm guessing that there must be a gauge fixing gone into the Hainaut-Teitelbaum form.
Or maybe it's not diffeo invariant. I will have to check. Because yeah, this is a scalar and this is a scalar, so there is no volume element multiplied to the term.
So first term is not a scalar. Root of minus G.
No, sorry. Yeah, I mean this.
Yes, but when you go to the tree form for a version of it here, and the bottom line, the Hainaut-Teitelbaum, now that looks fine. This one is diffeo.
So something has happened in going.
Exactly. That's why I'm thinking the gauge fixing happened in going upward.
Okay.
No, the star where you get the tree form should involve the square root of the metric, of the determinant of the metric. tau mu is a scalar tensor density, vector density.
Yes. Yeah, that's right. It's not exactly a vector, it's a vector density.
Vector density.
But if I start at the bottom, Ricardo, if I start with the one with A d lambda.
Oh, that's cool.
That one is cool, exactly. That's where I want to start. Now you have to start gauge fixing that to try and get to her action, because that looks like the natural place for me to begin.
Can I, while I'm at it, ask a question? In the
Please.
Padua group action,
Yes.
there was a term that seemed to be like a kind of a Nambu-Goto term, and that in a way perhaps fixes some volume in superspace.
Okay.
The last term.
So
Really?
yeah, sorry, yeah. Here, are you talking about this term?
Yep.
Yes.
Yeah, that's right.
Okay, so what's the question?
So in a way, this kind of fixes the volume. So I'm looking for some geometrical reason for why you find a coincidence. Looking at invariants, this is a natural invariant in this context, because then you have the embedding written on the bottom of the slide.
Yes.
And that in a way fixes a volume.
Yes.
In, I don't know what exact space.
Just super space, n equal to 1.
Superspace, yes. And I'm wondering if there is, if you have thought about this kind of correspondence in more geometrical terms, rather than by finding a coincidence at second order perturbation.
So yeah, first we just wanted to check if these actions are actually the same. I mean, until we don't know if they are the same, it won't be very practical to find a relation between them, because if they are different, then there probably is no relation between them, or it's not so easy to find. But if they are the same, then we'll be more hopeful to find the connection, a geometrical relation between them.
Thank you.
Yeah, sure.
I think Venus has some questions.
I do, yeah, but they're very naive, okay?
That's okay. All of our questions are naive at one level or another.
Yeah, so a lot of these concepts are just new to me. Could you go, starting from the beginning,
Sure.
to the unimodular gravity that you had?
Yeah.
I just want to look at the action and see. So again, I'm trying to understand it. This is good. Yeah, I'm trying to understand the concept of particle physics. So from this action, this is probably, I don't know, relevant for Paul as well. So phenomenologically, if you want an inflaton candidate or an inflationary kind of framework in this model, you would need a scalar field that is multiplied by the Ricci scalar, which you don't have here, right?
Yeah.
So if your model allows you to introduce something like that, then your model could incorporate inflation. And then if that particular field, best models of inflation in agreement with data are kind of the Slurl inflation type models where you've got a scalar field that kind of has a non-minimal coupling to the Ricci scalar. And if there is a symmetry in your model that protects that scalar from decaying, that could later on be your dark matter candidate as well. I don't know if your model could incorporate something like that or not, but
yeah, it can in principle. So near the end of my talk, one of the possible future research directions that I talked about was constructing phenomenological actions using this pure DS actions in inflationary cosmology. And the way we intend to do that is by coupling the pure DS action to scalar fields and matter. Yeah.
So that would probably be, I don't know, a phenomenological direction to go. But now my stupid questions. So here, what I was asking before. So once you've got this extra term that contains the epsilon 0, that is kind of your explicit breaking of the symmetry. But then later on, when you put the unimodular conditions in, you kind of spontaneously preserve the symmetry, or you symmetrize your model in a way. And then so that's again something that has implications for the real world, for example, that you would have these different transitions, and you don't necessarily have to, like, as the universe evolves, you don't necessarily have to break the symmetries. Sometimes also, depending on, for example, if you're looking at inflation, depending on what is your inflationary direction, which is the direction along which your inflationary potential reduces the fastest, then you could also restore some symmetries, which would actually be very interesting, because, for example, if you have an inflaton which is not necessarily conserved by a symmetry, but later on, if you restore that symmetry, or a symmetry that would protect that scalar from decaying, then that particular scalar could become your dark matter candidate, which is
that's very interesting.
Which is, I mean, it is quite interesting. I don't know of anybody having done anything like that. You start with, let's say, if you want to do inflation and dark matter in the same framework, you start with a scalar that is protected from decay. Then you kind of refer to the cosmological constant, but the cosmological constant was basically the way you would get it. A non-zero cosmological constant was through some of your fields getting a, did you call them vacuum expectation values?
Yeah, right. Yeah.
So
yeah, these are the background, the Webb's vacuum expectation values. And these constants here, K2 and K0, they first appear in the boundary conditions for the components of the Lagrange multiplier, which are given by. So these constant K0 and K2, they appear for the boundary conditions of these components of the Lagrange multiplier superfield. And then they come here.
So they come out naturally. It's not a condition that you impose.
Right.
I see. Okay. Because obviously if there's 0, then you don't have a cosmological constant.
Yeah.
That makes sense.
There is a paper, there is a work by Raphael Sorkin on this cosmological constant. Okay, he has argued and developed the idea that it is in quantum theory, it is dual to the volume of the universe. So there is an uncertainty principle, and he has used it to argue why you may get a positive cosmological constant, and how there can be fluctuations in this constant. So it doesn't start from d zeta or anything like that, but it starts from a unimodular gravity. And then he has a formulation where it is dual to the volume of the universe, and he infers properties of the cosmological constant thereby. And he thinks that is one of the strongest ideas for his causal set program. He has argued many times. Okay? I think Denjo will support me.
Yes, I mean, the way I would phrase it is that he thinks of the cosmological constant as a chemical potential for the volume element.
Except that there is an uncertainty principle. Normally,
But
there is
he,
none.
exactly, yes, exactly. Well, the point is that it's the uncertainty principle. I wouldn't quite describe it as an uncertainty principle. There is the volume elements is, if in a discrete theory, is accounting. It's if you've got a discrete theory with a finite number of volumes and a density for your volume elements, then the volume just comes with counting, and the Lagrange those will naturally fluctuate. So fluctuations in the volume would be related to fluctuations in the cosmological constant, as in the Lagrange multiplier should equally fluctuate in a natural sense.
There are one more couple of things. First, there is, in the same context, there is I think, a very beautiful paper by Doppler and I think Fredenhagen, which start from non-commutative geometry and find rigorous uncertainty principles for volume forms, area forms, volume forms, and so on. And I remember that they had a very rigorous lower bound, which I don't remember the formula, for the 4 volume form. By looking at it, one feels that there are applications. It's quite rigorous, but in
is this Doppler, Fredenhagen, and Roberts?
I think that is correct. Yeah, I have read that paper. It's a very beautiful paper where there is also a discussion of what is meant by observation. What do you mean by an event? They discuss it in a very logical way. Secondly, in this formulation, one talks about vacuum value, but what is a vacuum? There is no quantum theory. This is to Sukruti. When you write equations, what is a vacuum? Because you don't have, there is no quantum theory I see.
Generally, when we break supersymmetry, the vacuum energy is considered to be of the same order as the supersymmetry breaking scale.
To talk about it, you need a vacuum. So what is a vacuum?
Oh, well, the Lagrangian does not have any scalar or matter fields.
No, vacuum is a quantum concept, no?
No, I think she's using it in the sense that of a path integral, that there's a vacuum expectation value in a path integral, which I mean, I appreciate your point of view on it, but it's not so obvious what the quantum vacuum would be in that context. I mean, in some sense, it's whatever the ground state energy is, whatever the ground state of the system, that supplies the vacuum.
Yeah, but so to get the ground state, so this is the same thing as when you write functional integrals, that defines a state on the algebra. So functional integrals just defines the states on the algebra observables. Whatever one may take the statement, that is what it does. So one needs here a standard approach. You can talk about the minimum energy, for example. But for that, you need, as you say, a ground state energy. But we need the ground state. So what is the ground state? It is a quantum concept.
Okay.
At least I don't understand. I don't understand the statement. There may be some definition, but I don't know what it is.
I mean, it's going to be a general problem in any quantum field theory in curved spacetimes, I think.
Curved spacetimes, they don't, well, talk about these ideas, no? One doesn't talk like this. For people like Bob Wald, or you don't talk like, so you talk about Hadamard state on the algebra, and then you keep going. And in fact, yesterday,
it's like this is just the background values of the fields when you haven't excited the fields. You have not done any perturbation or fluctuations, so that the background values of the fields is what I call the vacuum expectation values.
Okay. So it's purely classical from what you say.
Yes.
I think that would be an equivalent way of saying the classical values of the fields would be an equivalent statement from our point of view. Am I correct, Sukruti?
Yeah, it's yeah, that sounds correct.
Okay, thanks. I think Werner was trying to get in as well. Just no. Okay.
I have another question if
Yeah,
nobody else does.
please go ahead. Go ahead.
So again, particle physicists trying to understand what you're doing. So here, first of all, what are the dimensions of these K0 and K2?
You mean like in terms of the length and mass dimensions?
Yes. Because you've written the cosmological constant, it's come out as something times K minus K0 squared. So do K0 and K2 have different dimensions?
Well, I'll have to see. Basically, they have the same dimensions as lambda naught and lambda 2,
okay,
which I think have, so they are scalars, of course. Yeah, I would say, I think the dimension, they're just like constants. I cannot tell the exact dimension off the top of my head, but given that these are scalar fields,
so the thing is that the way I understood, can you go back to the slide we were looking at with the cosmological constant? Yeah, here. Like that notation to me means the vacuum expectation value of lambda 0 is K0.
Yes.
So I wouldn't, again, to a particle physicist, it means that it has dimensions of mass.
Yeah, I think that's her cosmological constant, the way she's using it, has dimensions of mass squared.
But,
it has the same dimensions as the Ricci scalar, which is mass squared in that.
Okay, so K2 would be mass squared as well, right?
K2 is mass squared, and little m is mass.
Yeah. So now, again, I'm trying to connect it to the world I know. In the particle physics community, we've given up on supersymmetry because we can't find it anywhere. So, and of course, you can't rule out supersymmetry. You could always say, you know, it's at some high order that is experimentally inaccessible to us. So that means these K0 and K2 must be very, very large numbers. Is that correct?
Well, for that would mean that the supersymmetry breaking scale is very high. Yeah, right. Yeah, so they will have quite large values.
Okay, and that doesn't violate anything in your setup.
No. So basically, lambda 2 is the SUSY breaking scale, and yeah.
Sorry. It seems to me that unimodular gravity support only traceless equation of motion. That's why I was thinking before about the Weil symmetry, because also if I put also this file on in the chat. So it seems to me that if you want to add matter, it should be you know, traceless matter, so matter conformal matter, the only things that is compatible with unimodular gravity. That's why I was thinking maybe also the dilaton is not allowed. I mean, by adding the dilaton, I guess you break the symmetry, and okay, you move into a different regime. So that's why I think that this Weil symmetry has a certain relevance in this context. I mean, at least if we talk about matter, what kind of matter is allowed in unimodular gravity?
Yeah, okay, yeah, that's a good point. Maybe if the Lagrangian is supposed to have conformal symmetry, then a dilaton cannot simply be naively be
exactly. And or you can say also in an opposite way, if there is a dilaton, then that thing breaks conformal symmetry. So somehow it's a way to, you know, to break conformal symmetry by adding a dilaton, let's say. I don't know, this was just a thought, because it seems to me that the symmetry are only compatible with traceless stress energy tensor, and also that Ricci is traceless. So it's because of the unimodular condition on the metric.
Yes. Thanks.
I just had a very quick look at your at the reference you put in there. It looks like they are augmenting the unimodular one with an additional, some additional field. Is that correct? They have this G field, which is they're incorporating the scalar field associated with the determinant as an additional field.
Yeah, exactly.
So there is an extra field put in, which you can do, yes. But it's more than unimodular gravity. I mean, it's interesting, yes. That looks interesting. It could be quite related.
Okay.
So yeah, the statement is you can add an additional field which has which promotes it to have some Boyle invariance.
I love the abstract on the paper Jian shared. It's just one sentence. The symmetries of unimodular gravity are clarified somewhat.
Actually, I can say I'm interested in these stories because for application in condensed matter. So that's why I was looking previously to this unimodular gravity. Actually, because the area preserving diffeomorphism plays a very important role in interacting quantum systems. That's just why I was.
I mean, it's very interesting. Yeah, I learned a lot from these discussions, and it's so cool that everybody's from a different field, and you kind of understand the big picture a little bit better. Thank you so much, Sukriti. That was a fantastic talk, and I learned a lot.
Thank you.
Yes,
I'm happy to know that.
Thank you, Sukriti. That was excellent. Are there further questions? We don't. If there aren't, I will stop the recording and we can be a little bit.
Yeah.
Relax. Okay.